Till now, we have discussed the contiguous memory allocation using the method of either fixed partitioning or dynamic partitioning. In the fixed partitioning scheme, we have the problems of both internal fragmentation and external fragmentation. To solve the problem of internal fragmentation, we go for dynamic partitioning. So in dynamic partitioning, internal fragmentation is resolved, but the problem of external fragmentation still exists. Why? Because we are using contiguous memory allocation. So wherever we have fixed partitions, we will have the problem of internal fragmentation there, and wherever we have contiguous memory allocation, we will have the problem of external fragmentation. The one way to solve external fragmentation is using compaction, but it is not a preferred method since it is highly time consuming. So what is the other way to solve external fragmentation? We should go for, instead of contiguous memory allocation, we should go for non-contiguous memory allocation. If there is no requirement that the memory allocation should be contiguous, then we will be able to solve the problem of external fragmentation. And in non-contiguous memory allocation, we can use the method of either paging or segmentation. So first, let's discuss what is paging. To implement the non-contiguous memory allocation using paging, we divide our secondary memory or the logical memory into blocks of fixed size, small blocks of fixed size, and each such block is referred to as a page. Similarly, we divide our main memory or the physical memory into fixed sized blocks, and each such block in the main memory is referred to as a frame. So in secondary memory, we have the blocks, each is referred to as a page. In secondary memory, we are having pages, and in the main memory, we are having frames. And the size of the page will be equal to the size of the frame, such that each page can fit exactly into this frame, any of these frames. Assume the page size is 4 bytes, hence each page can hold 4 bytes, and the frame size is also same, it is 4 bytes. Now suppose we are having one process P4 residing in the secondary memory. The size of the process is 16 bytes. The size of each page is 4 bytes. So how many pages will be required for this process? 16 by 4. 4 pages will be required for this process. Hence, the process P4 will be covering 4 pages of the secondary memory. We can name it as page 0, page 1, page 2, and page 3. Now assume that we have two processes P1 and P3 which have already been loaded to the main memory. So in the beginning, the main memory, there will be enough space in the main memory so that sometimes the processes may be allocated contiguously. So assume that here the process P1 and P3 have been allocated contiguous memory space. Now a new process P4 is waiting to be swapped into the main memory. So what is the size of the process P4? It is 16 bytes. So what is the free space available in the main memory? Each frame is 4 bytes and 4 free frames are available. Thus, here we have 8 bytes free and here we have 8 bytes free. So for this process of 16 bytes, there is sufficient memory space of 16 bytes available in the main memory. If we are using contiguous memory allocation, will we be able to load this process to the main memory? No, because the available memory space is not contiguous. It is fragmented across two parts of the memory, and here there is external fragmentation. So we cannot load this process if we are using contiguous memory allocation. But by using paging, we just have to check. Here for the process there are 4 pages, then whether there are 4 free frames available in the main memory or not. Yes, there are 4 frames which are free. Thus each frame can hold each page. Thus we will be able to load this process to the main memory. Then each page of the process can be loaded to any of the frames available, even the order doesn't matter. So suppose page 0 is loaded to this frame. This is frame number 0, 1, 2, 3. So this is frame 3. And suppose the page 1 is loaded to this frame, and this is 4, 5, 6, 7, 8, 9, 10. This is frame 10. And let the page 2 is loaded to this frame. This is frame 4. And page 3 is loaded to this frame, and this is frame 9. Hence, the problem of external fragmentation is solved. The process is not contiguous. The process P4, which is residing in the main memory, is not contiguous and also not in order. Here the first 4 bytes and the next 4 bytes is present here, and the next 4 bytes is present here, and next 4 bytes are loaded here. Hence, the problem of external fragmentation is solved. But what about internal fragmentation? Assume that the process P4 is, instead of 16 bytes, it is a 13 bytes process. Then it will require 3 pages completely. That is 3 into 4, 12 bytes, plus 1 byte, 1 extra byte is required for the process. Hence, one entire page will have to be allocated for the process, but the process will occupy only 1 byte of this page. Hence, the remaining 3 bytes will be free. So while this process is being loaded to the memory within this frame, the last 3 bytes is free, and we will not be able to use this memory. Hence, within this fixed block or within this partition, we have a wastage of memory, and that problem is called internal fragmentation. So in paging, we have the problem of internal fragmentation if the process doesn't occupy the entire pages, that is, if the process doesn't completely occupy the last page. And to solve this problem, or to reduce this problem of internal fragmentation, what we have to do is we should reduce the size of the page, and hence we should reduce the size of the frame. But reducing the size of the page will increase the overhead to keep track of the pages and the frames, and hence it will affect the efficiency of the system. Hence, it is not a desirable method to reduce the page size beyond a particular limit, but if we increase the page size, we will have the problem of internal fragmentation. But the problem of external fragmentation is completely resolved, and compared to the advantages, the problem of internal fragmentation here is not much considerable.